Welcome everyone. My name is Lasse Peters, and in today's talk I'm going to present to you our approach for inferring objectives in continuous dynamic games from noise-corrupted partial state observations. Robots deployed to the real world do not operate in isolation, but they must interact with other agents such as humans. In these shared environments, the decisions of multiple players are often closely coupled. For example, in the highway driving scenario shown here, the driver of a fast car approaching from behind may abort their overtaking maneuver if one of the slower cars pulls in front of them. Dynamic game theory provides a powerful mathematical framework for reasoning about these coupled decision-making processes. In order to model a given problem as a dynamic game, two pieces of information are required. First, the dynamics f, which characterize the evolution of the joint state x, and second, the cost functions ji, which encode the objectives of every player. Using this game-theoretic description of the problem, we can predict player behavior for arbitrary initial conditions by solving for equilibrium strategies. While this mathematical framework is very powerful, it can be challenging to specify player objectives which accurately capture desired behavior. To address this issue, in this work we present an approach for identifying player objectives from observed interaction. That is, for a given sequence of partial state observations y and prescribed dynamics f, we attempt to find those player objectives which explain the observed behavior. This problem is commonly referred to as an inverse dynamic game. We formulate the inverse game as a constrained optimization problem with decision variables for states x, inputs u, and cost parameters theta. The objective of this estimation problem is to find a state input trajectory that maximizes observation likelihood. However, we impose the constraint that this trajectory is also the solution of a game with costs parameterized by theta. As a result, this formulation estimates states, inputs, and objectives jointly in a tightly coupled fashion. In order to tractably encode the equilibrium constraint, we relax it to require only local optimality of the observed behavior, and thus replace it with the corresponding first-order necessary conditions. Furthermore, in the case of Gaussian observation noise, this problem can be cast as least squares estimation. So, to summarize, our method can be understood as guided equilibrium search, where the constraints encode the root finding problem for local Nash equilibrium, and the objective guides the solution towards the observed behavior. Note that this formulation can be directly encoded by existing modeling languages for constraint optimization. We evaluate our method in a Monte Carlo study in which we measure the estimation performance for varying levels of observation noise. In this experiment, we compare against a baseline that estimates states and objectives sequentially instead of jointly. This figure shows the estimation error of both methods in parameter space for the highway driving scenario introduced earlier. The results show that our method, here shown in blue, identifies the true objectives of observed players more accurately than the baseline. We also evaluate the position prediction performance of both methods on the same dataset. For this purpose, we solve the forward game corresponding to the estimated objectives and measure the absolute error of the predicted trajectory. This evaluation in trajectory space shows an even more pronounced advantage of our method over the baseline. Overall, the results show that our method is suitable for downstream trajectory prediction tasks. To summarize this work, we have presented an approach for inferring objectives in continuous dynamic games from noise-corrupted partial state observations. Our method estimates objectives and trajectories of players jointly by maximizing observation likelihood while enforcing equilibrium constraints. The experimental results show that even in the presence of noise, our method can predict player objectives and trajectories with high accuracy. The code for our work has already been released on Github. Please feel free to give it a try. Thank you.